All right, how's it going, guys? So in this video, I'm just going to go through how you might think about the torsion bar, so part 2 of the project. So let me get that up on the screen to start with. Okay, so hopefully, yeah, so you should be able to see that. So that's the project, part 2. Should have seen that before. So we've got this torsion bar, simplified version of what I've shown in the pictures up here of the little open wheel racing car. For those who are interested, it's a Formula Ford. Yeah, anyway, so this member here that's curved around here is the ARB, or anti-roll bar. And I've just simplified it so you don't have this curved section to deal with, just so you've got a square section. So all you need to deal with is torsion of this section between the bearings and bending of the lever. Okay, so being able to analyze the deflection of this curved section here where you've got combined torsion and bending is beyond the scope of this subject. So that's why I've simplified it to this. All right, so I'm going to stop sharing screen and come back to me again. All right, so basically what we've got there is a U-shaped structure, something like this, and forces at each end in opposite directions. In that orientation, it's a bit hard to see that what's happening there. So, and unfortunately, the thicknesses of these the levers on this are a bit thin, so you might struggle to see it. But I'm going to do this anyway. So, if I apply forces with my index fingers in opposite directions, we'll see what's happening. All right, so we're getting twisting between my thumbs. So my thumbs are acting as the bearings and my fingers are acting as the loads, causing twisting of the shaft or twisting of the torsion bar. And on top of that, or superimposed on that, we've also got bending of the levers. Okay, so you need to superimpose the rotation of the levers due to torsion of the shaft or the torsion bar, and the bending of the levers. All right, so we'll have a look at, I'll share my screen again here, and we'll have a look at the model that I've got here. So there's 3 ways that you can look at the problem and look at deflections and the relative deflections that are going on. There's probably more than 3, but 3 main ones. So the first approach is, can't click there, I need to click down here. So I've just redrawn the model here, and to just look at the deflections going from one end to another and choose one point in the structure as your reference location that doesn't move. Right, so here in this one, I'm going to say, let's think about that we're getting bending in this lever CD. Right, so if we look at this from the side, right, and we're pushing down on here, let's push from the front, right, we're getting some bending there, right? All right, so hopefully you can see, I don't want to switch in and out of sharing screens, but hopefully you can see what's happening there. Right, so we're getting some bending there without considering what's happening in the section C to B, the torsion part of the torsion bar. All right, so we've got that vertical deflection, and you can model that using, I'm going to just go back the page. All right, so you need to look at these and say, well, which one do these standard deflections, which one of these standard deflections can I use to model that deflection? Okay, so if I'm doing this, again, looking at me in the side, over in the side, pushing down on here, hopefully you can see that that's what we've got here, right? Or we can model what's happening in the torsion bar with this. So at was the It's gone off screen. Okay, let's, whatever that was called, right at that point here, that I think it was called C on my diagram. It's a continuous connection here, right? It's not hinged, so we can treat it as, or we can model it as built in to the rest of the component, right? All right, so let's go back over here. Yep. All right, so we've got that vertical deflection, and we can calculate that using the standard deflection formulas that we looked at in that table just before. Okay, so let's move on to thinking about what happens to the section CB. So now we're holding it, or we're considering it that at point C, it's not moving there, and we've got a force at, let's flip that over. There we go, pushing up. Okay, so these bearings, right, provide lateral reaction forces, but they're bearings, so it's free to rotate. Right? So this particular problem that we've got here, in terms of thinking about equilibrium, it's unstable equilibrium, right? So for this to be an equilibrium, if you took moments about the axis through CB, right, PA, and these lengths LAB and LCD are the same, then PA must be equal to PD, right? So you need to draw your free body diagram, do your sum of the torques or sum of the moments equals 0, and show that PD is equal to PA. But it's unstable equilibrium, right, with just forces like this. If we had PA plus a little bit, right, and PD stayed the same, then we'd start to rotate. Anyway, if we continue our thinking here that we've treated C as the stationary point, and thinking about what's happening from here to the rest, through the rest of the structure, right? So CB, I think you'll agree, if we apply those loads, is going to twist. We're going to get twisting in the torsion bar from C to B. So if this section twists, then this part BA, without thinking about whether it's bending or not yet, is just going to rotate, all right? So support it at one end and then just push it up on the other end. The torsion bar rotates. So if I do that, okay, let's see, like that, right? If I apply a torque just at the end B, right, you see that rotates. Right, that lever rotating because I've applied a torque at the end of torsion bar. Okay, so that's what I'm showing here. Right. And that rotation here is the angle of twist that you calculate for a shaft in torsion. So you would have seen that before and in my exemplar. So let's find that exemplar. Right, so I've shown you here for my exemplar using a T-bar. The angle of twist is TL upon GJ, right? So you would have seen that in the lectures and in the tutorial problems. Okay, so that gives us that. And then from trigonometry, we can get how far this moves, right? So if it's small angles and this angle is in theta, is in radians, then this displacement here is just the angle times this length here, length AB. Okay, oops, click here. So that's what I've said there, vertical deflection of A due to the rotation of AB, and that's just simple trigonometry. All right, so then, right, so we've got to the point where we've got torsion being applied to shaft or the torsion bar CB, and AB is just rotating along with that, but we've actually got a force acting out at the end here at A. Okay, so on top of that rotation, we're going to get superimposed that deflection or that bending deflection, right? And again, we can model this in the same way that we did from C to D, using that standard beam deflection from the table. Okay. Oops, wrong play button. Okay, and I've written that in there. Okay, so if we go to my exemplar that I've given you, so the blue dotted line here is the rotation of the T due to torsion of the vertical torsion bar in this case, right, which we calculated here. And then superimposed on top of that is the deflection that occurs in the two parts of the T. Okay. And you can, again, model that. All right. All right. Let's go back to here. All right. Again, press the wrong play button. All right, so let's have a look at that from the side view, and see if I can make that a little bit clearer what's happening. Okay, so jump 2 steps there. Let's jump back 1 step. All right, so we've got the deflection downwards of CD due to bending. So we're now looking at this end, right, NCD, and then we've got at the other end the rotation of AB due to just the torque being applied to CB. So if I do that, there's no force on the ends of those levers, looking at me on the right hand side, and we get twisting at each end, and each end moves away from each other due to that torsion. All right, so here we're treating the whole length CB to work out this angle of twist. And then superimposed on top of that, maybe, there it is, we've got the bending deflection over here. Okay, so the total deflection between points A and D is from here at the top down to here. Okay, so that's approach 1. Let's have a look at another way of thinking about doing this. So approach 2 says, all right, these forces have to come from somewhere. Let's now treat point D as the stationary point, the point that doesn't move, and work out what's going on in the rest of the structure or the structural component relative to that. So we can say that, let's imagine that this force PD here is the reaction force that's generated by a pin connection at D. Okay. Now we can work our way through the structure again. So if we look at what's happening here, let's say we've got this force PA out here, and I've just moved the label away to fit in some deflection diagrams further on. But yeah, so if we have this generates a torque through here, which is a moment acting on the end of this lever CD. Okay, so that will bend it up. So if we go back to that, this one's a bit tricky, right? So I didn't expect people to come up with this on their own. This is a bit tricky, but I thought it worth showing you to see how you can make use of these standard formula and also to understand the superposition of deflections and how to model connections between things. So what we're doing here is actually using this one here. So we're looking at lever CD as a simply supported beam with a moment at the end. Okay, so this moment now is being generated by this rest of the torsion bar at the end. So if we're looking here at as our simply supported beam, and it's really hard for me to do this. If I apply that load there, yeah, I can't do it. Haven't got enough fingers and hands. Yeah, so this is just a little bit tricky. If you don't get it, that's fine. It's just something to think about and maybe have a go at trying to work through later if you're really interested in trying to understand this stuff. Also, you don't have to do all three ways in your project. Just choose one way and do that, and submit that. I'm only going to mark it on one way, but yeah, as a challenge and extra learning for you, if you really want to try and understand this stuff, then have a go at doing all three ways. But yeah, as I said, you don't have to do it for the project. All right, so let's go back to where we were. Okay, so pushing up on here, that rotates up here, that causes a torsion through here and a moment and generates this deflection from C to D. Okay. All right, so I'll just put in there. Yeah, so I'll just put that, what I've just talked about. All right, so now it starts to get even trickier. All right, so what we need to calculate from this part of our modeling is the slope at NC, okay, from that standard deflection that we looked at before. Okay, so if we get that slope here at C, then the rest of the torsion bar rotates relative to CD, that amount of rotation. Okay, so over at A here, we get this end A move up due to simply the rotation that's generated relative to the connection here at C. Okay, and to get this deflection, again, it's just simple trigonometry for small angles. If this is in radians, you can just multiply the angle in radians by the length here to get this deflection. Okay, wrong play button. So I'll just put that there, and I'll just put those words there for you. Okay. Yeah. So, right. The next thing we need to look at is on top of this, we get twisting of the shaft, right? So, as well as this bending of CD, we get twisting of the shaft, right? So we need to add that into our deflection model. Okay, same as we did previously. So again, we get this angle just from the torsion. Go to our exemplar, right, just from this equation. Right, and then we can multiply by the length to get this deflection here. Okay, same as we did previously. And then on top of that, we have the bending of B to A. Okay, so put that in, and the vertical deflection of A relative to B due to just the bending of this. Okay, so we've bent one end, we've twisted the torsion bar, it's rotated to here, and now we've got bending on top of that. Okay. Pushing up here, we get that bending in that rotated position. and calculating that is the same as we did before. Okay. All right, so if we look again from the side view, we get the bending here and a slope. Okay, so rotation of C to B and B to A. Right, so that's the rotation that we get from that bending. Then on top of that, we've got the rotation due to the twisting of C to B. And then on top of that, we've got the bending of B to A. Okay. And this deflection here should be the same as from this to here. Okay. All right, that's approach 2. Approach 3, there's that, right? If I'm applying equal and opposite forces, right, after we've done our sum of the moments about C to B equals 0, we'll get that P is equal to PD. And if we apply that those forces, and they're all balanced, then, well, firstly, we can look at this structure and see that it's symmetrical. Right? So at the plane of symmetry, we should know something about what happens at the plane of symmetry. But our forces here, or our loading on this structure, is anti-symmetrical. Now, again, this is beyond the scope of this subject, but you may have gotten to this way of thinking intuitively. Right? So if we redraw our torsion bar here, and we say we've got a plane of symmetry here, and we look at this and we do that at each end, right? It's hard to see on my little thing here, right? But relative from one end to the other, right? This should move up the same amount as this moves down. This should rotate up the same amount this rotates down. So we could look at just half of the model. Okay. So if we do that, so I've just put in there, that's a plane of structural symmetry, but the loading is anti-symmetrical, so you need to be careful. And then we look at over here. So relative to this plane of symmetry, or really anti-symmetry, because the loading is anti-symmetrical, we get rotation of AB due to angle of twist of half of CB. Okay, because if you imagine this rotates up a certain amount and this rotates down, at the plane of symmetry, we have 0 rotation. Yep. So then from that, so if I could take half of my torsion bar like that, at the C, right, and then I'm just applying that force to just half of it. Like that. Right. Also noting that it's in a bearing here. Right. So we've got the torsion or the rotation due to the torsion of CB, or half of CB. The deflection just from trigonometry as before. And then superimposed on top of that, we have the bending of B to A. Okay, and that extra deflection here. And again, we get that deflection from modeling it as a cantilevered beam from B to A. Okay, so you could just stop there and say that the stiffness is this force over this deflection, or you could, I'll just put in there vertical deflection due to bending, as I discussed, or we can look at the other end, right, and add that deflection for the whole length. Okay. All right, so if we look at, again, from looking at it from the side, oops, let's go back and do that step by step. All right, so we have from C to D, rotates down, and from B to A, rotates up the same angle, okay? Because we're modeling it as anti-symmetry. Right? So if it was symmetry, we would just mirror what from one side to the other. But for anti-symmetry, you mirror from one side of the symmetry plane to the other and then change sign. Okay. So here, rotation down on this side of the symmetrical plane or anti-symmetrical plane becomes up rotation on the other side. And then we have our deflections on top of that. So our total deflection from one end to the other is, or should be, the same as what we had before, right? So from here to here for approach 2, and for approach 1 from here to here. Those deflections total deflections should all be the same. Okay. Now, I don't mind which approach you use, as long as you're clear in your diagrams and explaining what you're doing. Okay, did I want to say anything more at this point? I think that's enough for this. This is nearly 30 minutes already. So I'll leave it there. And yeah, I'll post this, the PDF of the notes that I've just gone through on Canvas via MS Teams. All right. Hope that helps. I know it was a little bit advanced, some of it, but as long as you understand, the first approach is probably the easiest. So if you can do that, then that's fine. All right. See you in the next video. Bye. Or in the next. No, we don't have any more classes. We're done. Okay.